So the question is, if we can't plot these complex numbers on the real number line, where are they? Because like I said, they do exist. Well, if they're not on the number line, where are they? And the answer is, well, they're above and below it. It's sort of like, imagine the ground is the number line, then the air that we're walking through, that's where all the complex numbers are. You're walking through them. Right? Now, we have a convenient diagram to represent it. We call it the Argand diagram, probably named after the person who came up with the idea. Diagram. Now, we can represent it on the Argand diagram, and it looks surprisingly familiar. There it is. For all intents and purposes, it's the number plane. But now the x-axis, instead of calling it the x-axis, we call it the real axis. Just like we used to see. The number line we normally see horizontal. And then coming up through it, through 0, we now have an imaginary axis. Okay. So if I want to find the real number 2, it's no different. I plot 2 on the number line. There it is. Okay. But if I want to plot minus 3i, well, that one's purely imaginary, so it'll be lying on the imaginary number line, or the imaginary axis, down there at -3. And if it's a mixture of the two, just like coordinate geometry, the real part is the x value, if you like, and the imaginary part is the y value, so C would be the point -2, 1. And there it is, sitting above the real number line. 4 minus I would sit below. There it is, over there. 4 plus I would be above. And this brings up the first interesting relationship when we're looking at something as a picture rather than a piece of algebra. When we look at the Argand diagram, conjugates will always be reflected in the real axis, because the only difference is the sign of the imaginary part. So you'll always see that reflection. Now, if I get the point -4 plus I, which is the negative of D, well, how does that sit? Well, let's plot it. There it is. It's reflected through the origin, like an odd function, if you like. So if you were to rotate it 180 degrees, so that multiplication of -1 is rotation of 180 degrees, which brings us up to the next idea. If I was to multiply it by I, now, we just said if we multiply it by -1, we rotate 180 degrees. Well, multiplying by -1 is the same as multiplying by I, then multiplying by I again. So we did 2 even rotations and got 180 degrees. Therefore, one of those rotations must have been 90 degrees. And so there it is up there, plotted, and sure enough, it's a rotation of 90 degrees. Okay. So that's what happens when we multiply by I in the picture. The point gets moved 90 degrees. Now, the beautiful thing about this is it means every complex number has a unique position on there. Because at any point, there's only one complex number that could go there. It has to match up the real and the imaginary part. So we now have a visual way of representing numbers, just like we did with the number line. So this brings up a fun thing, locus. I know we love locus, however you say that word. If I want to express a horizontal and vertical line, now, so there's a horizontal line. Yes, in coordinate geometry we'd call it y equals c. Well, when we're talking about the locus of a complex number, what's y? Y is the imaginary part. So if they said, well, draw the picture or draw the locus of the imaginary part of z is equal to c, that's what we're drawing, y equals c. So every single complex number on that line would have an imaginary value of c. And so a vertical line then, well, they all have the real part in common. So it would become the real part of z is equal to some constant value. Circles then. Whoop, there's a circle. So every complex number there, what has it in common? Well, remember what we said about z times z conjugate? Remember how that turned out to be the sum of two squares, x squared plus y squared? hang on a sec, equation of a circle. X squared plus y squared is equal to some constant. So a circle then must be that z times z conjugate is equal to the radius squared, because that's x squared plus y squared equals the radius squared. So what do they have in common? Every single complex number on that circle is the same distance away from the origin, whatever the radius happens to be. Alright, so let's describe these ones. Ooh. Z plus 4 plus I, Z conjugate plus 4 minus I is equal to 49. Now, of course, when you look at them, if you don't immediately recognise it, then what you do is you replace Z with X plus IY. But another way, because that can get the algebra a bit tricky, is I'm going to persevere and expand it even as we see it. So I get Z times Z conjugate, hang on, I know that's X squared plus Y squared. 4 plus I times Z conjugate, plus 4 minus IZ, and then we've got the difference of two squares, which will turn out to be the sum of two squares there. So I'll keep going. Eventually, I do sub in. So, I mean, that's up to you. Do you want to sub in the X plus IY at the beginning, or do you want to sub it in at the end? It doesn't really matter. But if you persevere with it, you end up with X squared plus Y squared plus 8X plus 2Y. Well, that needs some tidying up, doesn't it? So there we go. Let's group the X's together, the Y's together. We've got 16 and 1. Complete the square. Half of 8. Oh, that worked out nice, didn't it? They're already complete squares. How handy. And so we get X plus 4 all squared plus Y plus 1 all squared is equal to 49. Now have a look at the original question and have a look at the answer I ended up getting. So the reality is, I don't have to do that expansion each time, if you notice the pattern there. You see? It was Z plus 4. We end up with X plus 4. It was Z plus I, so the imaginary part is 1. We end up with Y plus 1. So I'm not looking at the conjugate part of it, because if you notice, what we've got here is Z plus a complex number, Z plus its conjugate. Oh, sorry, Z conjugate plus its conjugate. So I'm interested in looking at the bit that's not got the conjugate, and that tells me straight away where the centre of this circle would be. It's going to be at 4. Oh, actually, my mistake. It's not going to be at 4, 1, the centre, is it? Because it's always Z minus the centre. So the actual centre of this one is -4, -1. So there we go. We know the locus is a circle. Centre -4, -1. Radius would be 7. So in general, when you see Z minus a complex number, and then in the next parentheses you see the conjugate minus that number conjugate, you can end up with a circle. The centre will be omega, and the radius will be r. Okay. We will look at more of these later on, but this is just sort of, I guess, a bit of an introduction of them. Now, 1 plus Z plus 1 on Z conjugate is equal to 1. So again, I got no idea what that looks like. So let's get it in X and Y's there so we can come up with a Cartesian equation that we might recognise. Well, I'm playing around with it first before I sub in, so I've got rid of the fractions by multiplying everything by Z conjugate. So I get Z conjugate plus Z is equal to Z times Z conjugate. Well, Z conjugate plus Z would be twice the real part, so 2x. And Z times Z conjugate is X squared plus Y squared. It looks like it's another circle. Once I see that X squared and Y squared coefficients the same, I now go to circle. Let's play around with it. Move the 2x over. This time I do have to complete the square. So it becomes X minus 1 all squared plus Y squared is equal to 1. So the locus is a circle, centre 1, 0, radius of 1. However, there's the picture. There's something wrong. That is not the answer. That is not the answer to this question. What's missing? I've transformed it into something so I can recognise it. Remember, you always go back to what the original question was. The original question has Z on the bottom of the fraction. We know, again, the rules of maths don't change. The bottom of the fraction cannot equal 0. So z equals 0 is not a possibility. So when I look at my answer, whoa, hang on a sec, z equals 0 lies on that circle. So there must actually be a single point discontinuity there at the origin to answer the original question. And so careful with things like that. If you transform it into something else, you might create solutions that aren't actually part of the solution. So check, we're back to the original. Okay, so 1C in our Cambridge.